Hi everybody, this is Dr. Nigro with a Physics Fundamentals screencast. This one's going to be first in a series of screencasts that will deal with work and energy. This particular one is going to look at work when a constant force is being applied or is affecting the motion of our object. All right, so let's say that we have an object, we'll have a box. All right, and that object is in motion to the right, and there's a force that's being applied. All right, now I'm going to draw it angled, but it doesn't have to be. All right, if I want to determine the amount of work, all right, and work is the energy that's required or that's being used to start, stop, change the motion of a particular object. And work has a couple of requirements. We use capital W for work. You need to know what the force is, and it's going to be an absolute value. You need to know the displacement of the object, which means how far has it moved from its original position. And then we need to know the cosine of the angle. All right, now that angle theta, we've dealt with theta quite a bit. In this case, it's a little bit different. All right, theta is the angle between the motion and the force we are looking at. All right, so that force could be an applied force, maybe it's the gravitational force, maybe it's friction, maybe it's the normal force. It's basically looking at, well, if we know the direction of the motion, what is the angle between that direction and the angle that we are investigating? Okay. Work has its own set of units. Now we've got force times displacement, so that means we're going to have a unit of newtons times meters. All right, and a Newton meter actually has a different name. It's called a joule, which we represent with a capital J. All right, and I don't know if you remember, but back in chemistry, we learned that joule represents energy, all right, which tells us that work is energy. Now, it is a scalar quantity, so that's going to be a little bit different than force, acceleration, displacement, etc., etc. I'm going to move this guy. Sorry. Here, buddy. Go up there. All right. But it can be positive or negative. Now you might say, well, how is that possible? Because we've been using positive and negative signs to indicate direction. All right, well, here it's more describing energy being put into our system or object. That's going to be our positive values, or energy being removed. All right, and that's going to be our negative values. All right, so when we talk about work, we're really talking about the energy that these forces are providing that then cause that displacement. So that energy can either be added in, and when that happens, those forces tend to support that motion. And if they win, and by win I mean if the net force is positive, then that means the object should be speeding up. Forces can also be used to remove energy from a system. Friction is a great example. And if the net force is negative, meaning that friction is greater than our applied force, then we should see our object slow down. All right, so the sign of energy, the sign of work, is really telling us whether these particular forces, when they combine, are working to put energy in or take it out. All right, now with that idea, Fnet, we also do talk about the net work that's done on our system. There are two ways to calculate it. One, we could use Fnet. So say we look at our free body force diagram and determine all of the forces acting on our object. We can calculate Fnet, and then we can multiply that by the displacement and the cosine of the angle between that net force and our motion. All right. Or that net work could be the sum of all the work values that we calculate. All right, so very similar to adding up all the force values, we can calculate work for all our different forces and then just add those values together. All right, we're going to be doing a little bit of both. All right, but again, the formula is the force times the displacement times the cosine of the angle between the motion and that particular force. All right, so let's try a couple. All right, after Dr. Nigro's car broke down, she pushed it off the road while she waited for the tow truck. If she pushed horizontally with 225 newtons of force over a distance of 5 meters, what was the work done? All right, so we're going to have a new variable list. We're going to have force, we're going to have displacement, theta, and then work. All right, so let's see. We have 225 newtons of force, and we're going to move that object 5 meters. And horizontally tells me that the force and the motion are parallel to one another. And if that's the case, then my theta angle is going to be 0. All right, so we have work equal to the absolute value of my applied force times the displacement times cosine of theta. And we're going to get an applied work value here equal to 225 newtons times 5 meters, and then the cosine of 0 degrees, which is 1. All right, so we find that our work here is going to be equal to 1,125 joules. All right, so this means that if I need to move my car, it's going to cost me 1,125 joules to apply a force of 225 newtons and move that car in a parallel direction 5 meters. Okay? All right, now for part 2, friction is being exerted by the road in the tune of force of 75 newtons. So now what was the net work done on the car? All right, so I have 2 choices. All right, I can calculate Fnet and then calculate net work, or I could calculate the work done by this frictional force and then subtract that from the work I found up in part A. All right, so we know the applied force from the first part was 225 newtons. All right, I need to calculate, I've been given the frictional force at 75 newtons, and I know that my distance is 5 meters. All right, I think that what I'm going to do is calculate Fnet. All right, so I know that the net force is the sum of the forces. All right, so in the parallel direction for the motion, I've got an applied force and a frictional force. All right, that applied force is 225 newtons. And then my frictional force will be in the opposite direction, so we get a negative sign. And I'm going to have a net force of 150 newtons. All right, I then go to my work formula. This time I'm talking about net work, so I'll use my net force, my displacement value, and then the cosine of the angle. All right, now, because my Fnet is positive, it's in the same direction as my applied force, which we've already said is parallel to our motion. All right, so our theta value here is going to once again be 0 degrees. All right, so our net work is going to be equal to 150 newtons times our 5 meters times the cosine of 0 degrees. So that cosine, not 0, sorry, it's going to be 1. So we have a net work being done here of 750 joules. All right, so you can see that if we compare that to the applied work, all right, we've lost some of our energy, and that energy is being removed from our system because of that presence of friction. Okay. All right, let's look at the next one. All right, Dr. Nigro's car got stuck in the mud. Poor Dr. Nigro. How much force did she apply if she did 2,000 joules of work pushing the car, 1,250 kilograms, 5 meters? All right, so I've got a work value of 2,000 joules. I have a displacement of 5 meters. And the questions ask me about force. Now, it doesn't tell me anything about an angle. So I'm going to assume that we are working horizontally again, which is going to give me an angle, a theta value of 0. All right, so work, this is going to be applied, is equal to my applied force times my displacement times the cosine of my angle. All right, so we plug in 2,000 joules. We're going to have our applied force, and then we have 5 meters, and then a cosine of 0 degrees. That cosine of 0 is a 1. So I end up dividing my 5 meters over to the other side, and a joule is a newton times meters, and then I divide it by meters, and I have newtons left, and in this case, 400 newtons worth of force. So if I expend or put in 2,000 joules worth of energy to push an object 5 meters, then I have to be applying a force of 400 newtons. All right, let's try this one. Dr. Nigro pushed her lawnmower with 50 newtons of force over 200 meters to cut her lawn. If the force was applied at an angle of 15 degrees below the horizontal, how much work did Dr. Nigro do on the mower? Assume grass is frictionless, which is crazy, but it's just to make the problem a little bit simpler. All right, so let's see what we know. I have an applied force of 50 newtons. I have a displacement of 200 meters, and this time my angle is 15 degrees. All right, so that means that the applied force is not parallel to the motion. It is in fact at an angle. All right, so I will need theta this time. All right, and then the question wants to know, well, what is the work that we've done? All right, so we know work applied is going to be equal to our applied force times our displacement times the cosine of 15 degrees, theta. Do formula first. All right, so that work value is going to be equal to 50 newtons times 200 meters times the cosine of 15 degrees. All right, so I plugged that all into my calculator, and I find that the work that's being done by this applied force is 9,659 joules. Okay? All right, last one, number 4. So Dr. Nigro pulls a crate, 50 kilograms, across the floor, 15 meters at an angle of 25 degrees above the horizontal. If she does 1,700 joules of net work on the crate, what is her applied force? Assume friction is present, and we've got a mu, kinetic mu value here. All right, so I'm going to start this one with a free body force diagram because this could be a little complicated. All right, so we've got our crate. All right, I know because I've got an angled force. All right, that angled force is upward, which means I'm going to have an x component and a y component. That y component points up. So I'm going to have a normal force, but I'm also going to have the y component of that applied force helping the support force. And equal and opposite to the sum of those is going to be my gravitational force. So these three forces are equal and opposite. All right, I'm going to have an applied force x component to the right, and because the problem tells me I've got friction present, opposing that force is going to be my frictional piece. All right, now I'm going to write my Fnet formulas for that parallel portion. All right, so first, that parallel motion, I'm going to have my x component of that applied force plus my friction. All right, and then my Fnet equation for the perpendicular forces, I've got 3. I've got my normal force, I've got the y component of the applied force, and I've got my gravitational force. All right, now for this perpendicular portion, let me get my favorite color for signs. There we go. All right, that normal force points up, so it's positive. So does that y component. Fg points down. And we know that the Fnet for this particular direction is going to be 0. All right, we know that because the mower is not floating or sinking, it's just going horizontally. All right, so that means I can rearrange, and I see that my normal force is actually equal to the gravitational force minus the y component of my applied force. All right, and why is that important? Well, I'm going to need it because I need to calculate Fn. Why do I need to calculate the normal force? Because I need to calculate friction. All right, so we're going to take a minute and just plug in just so we have that ready to go. All right, the gravitational force, we have a mass of 50 kilograms. We're just going to use 10 for gravity. So we're going to have 500 newtons for Fg minus that y component. All right, and that's going to be my applied force times the cosine of the incline, cosine of the angle at which we are being applied, which in this case, I just messed that up. I just mixed it up with inclined plane. Sorry about that. This is an angled force, not an inclined plane. All right, so the y component is the applied force times the sine of our 25-degree angle. All right. Okay, so now let's list out what else we know. We have a mass value of 50 kilograms. All right, we have a displacement of 15 meters. We have a net work of 1,700 joules. All right, we know that the applied force angle is 15 degrees, and we've been given the kinetic coefficient of friction as 0.2. All right, so that's what we know. The goal is the applied force. So I'm trying to figure out what is this applied force right here. All right, so I'm going to get at that by looking at the components. And this means that I'm probably going to have the unknown in two different spots, and I'm going to have to use algebra to solve. All right, but let's start with our formula. So the net work is going to be equal to the net force times the displacement times the cosine of our angle. Okay, so we're going to start by plugging in 1700 joules for Fnet. For work net. We don't know the net force. All right, we do know the displacement and we know the angle. Oh, this should be 25. Hold on, I put this wrong over here. 25. Okay, so we plug that in and solve for that net force. The net force acting on our object is 125 newtons. All right, so with that, I'm now going to go look at my Fnet equation. All right, so I know that that net force is also equal to the x component of the applied force plus my frictional force. All right, and I know that the x component is positive and the frictional force is negative. So I'm going to make sure I include those signs. All right, so let's expand that formula. I'm going to move down a little bit. So that net force, FAX, is also the applied force times the cosine of our angle plus negative kinetic coefficient of friction times that normal force. All right, so now I'm going to plug in numbers. So I have a net force of 125 newtons. All right, the applied force times the cosine of 25 plus a negative, and then I'm going to put in 0.2 for my coefficient of friction. And then for Fn, I'm going to plug in this piece, 500 newtons minus the applied force times the sine of 25 degrees. All right, so I can calculate the cosine and sine of 25 degrees and put numbers in for that. So I have 125 newtons, my unknown applied force times 0.91. All right, then a negative 0.2, I'm going to distribute this guy to 100 newtons plus that negative sign is going to also distribute. And then the sine of 25 is 0.42. All right, so I only have one unknown, this applied force. So now I need to isolate. All right, so I'm going to move this 100 newtons, the negative 100 newtons, to the other side. That's going to give me 225 newtons. And then I'm going to add 0.91 and 0.42. So that's 1.33 times my applied force. Then divide both sides by 1.33. And I find that my applied force must have been around 169.2 newtons. All right, so in other words, if I apply a force of at least 169.2 newtons at an angle of 25 degrees above the horizontal, in the presence of this percentage of friction, I will have a net amount of work of around 1,700 joules. Okay? All right, so this is just some examples of how to use that net work equation.